Okay, cancer. Despite all of the new treatments that are available, cancer is still on the rise in all developed countries. Cancer is so difficult to treat because it manifests in so many different forms and it varies from person to person. In fact, in Australia, it's been estimated that 1 in 2 men and 1 in 3 women will be diagnosed with cancer before the age of 85, so it's still a real problem. However, one thing that's true for all cancers is that the earlier that you can detect it and therefore start treatment, then the more favourable the patient outcome. So we all know we can use an X-ray to look for bones, but how do we look for cancer cells? Positron emission tomography, or PET, is one such imaging technique, and it's already being used in hospitals. A tiny radioactive probe is injected into the bloodstream, and this gives off radiation, which is then picked up by the detectors of a PET scanner. Now, this is perfectly safe, and it's such a great technique because it's so sensitive, so even a tiny amount of the radioactive tracer can be detected. However, there's one drawback. The most commonly used radioactive probe in cancer therapies today isn't cancer cell specific, and its effectiveness can vary on the size and location of the tumour. But that's where my PhD research comes in. I'm going to try and enable, by designing new radioactive probes, the easier visualization of cancer cells, and I'm going to do this by having a cancer cell-specific target. So my target is carbonic anhydrase 9, or CA9. This is a bucket-shaped enzyme which is produced by tumour cells, but is virtually non-existent in surrounding tissues. The tracers I have designed fit exactly into this bucket shape, much like a lock and key. At the other end of my key, this is where I have the radioactive part, which will give the signal to the PET scanner and allow us to build up a picture. So earlier this year, to show that this works, I conducted my first animal study. Human tumours were grown in mice, half of which produced this enzyme, CA9, the other half of which we engineered so it didn't. So if you just take a quick look to my slide, as you can see here, the mouse with the target enzyme, the area of the tumour is clearly highlighted and picked up from the surrounding tissues compared to when it's not present. But what does this actually mean for us? Over 85% of cancers are solid tumours and produce this enzyme. So this may mean that we can target cancerous lesions better than what's currently available. This in turn will then allow earlier treatment for patients, and this is all just simply by finding cancer faster. Thank you.